Welcome back. In the last part of this lecture, we're going to introduce the main theorem for the day, which is the derivative of an inverse function. This theorem's telling us basically how we can find the derivative for our inverse, as long as we know that f itself is differentiable, and actually that there's going to be a relationship specifically between the derivative of f and the derivative of f inverse. We already knew that if f was invertible and differentiable, then f would have an inverse that has a derivative, as long as f's derivative itself was not zero, right? That was the previous earlier theorem we had, that wherever f was differentiable and not zero, then f inverse would also be differentiable. So this theorem is now telling us we've got ourselves a nice differentiable function that has an inverse, and if you wanted the derivative of that inverse, then that would just be the reciprocal of the derivative of f. Specifically, if you're looking for the derivative of f inverse at x, then that's the reciprocal for the derivative of f evaluated at f inverse of x. We could sort of make this a little bit nicer and more obvious if maybe we just sort of said for ourselves if y was f inverse of x, then you could rewrite that relationship as f of y is equal to x. So that means that that derivative in the bottom is the derivative of a function in terms of y, or in other words, the derivative in the bottom would be the derivative with respect to y. So instead of being dy dx in the bottom, it's dx dy. So we have the derivative of y, the derivative of our inverse function is basically just the reciprocal of the derivative of our original function. So this is it in action. I mean, I know this is sort of an artificial example because we have power rule and we know how to deal with the derivatives of both x cubed and x to the 1/3. I just wanted to show that this previous theorem would still be consistent with what we would have found using power rule. So we know cube root and cubing that they're inverses of each other, and so let's pretend that we know how to find the derivative of x cubed, but let's pretend that we aren't sure whether or not power rule would apply to x to the 1/3. Let's pretend we haven't really proven it works for rational powers, just whole number powers. So the previous theorem would say, well, not a problem, because we know what the derivative of f is. The derivative of f is 3x squared. So by our previous theorem, if you wanted f inverse of x and you wanted its derivative, you would just say, well, it'd be 1 over the reciprocal of, it would be the reciprocal of f's derivative evaluated at f inverse. F's derivative, that was 3 times whatever the input is squared. So in this case, it would be 3 times f inverse squared. And f inverse, we set up here, that was the cube root function. So we'd really have 3 times the cube root squared, which gives me 3x to the 2/3. In the denominator, and that's exactly what I would have had I used power rule. So my theorem for the previous theorem, the telling me the derivative of an inverse, I get the same result whether or not I actually even knew what the function f inverse, what its derivative happened to be. So even if I didn't know how to apply power rule to this, I could still wind up finding its derivative. So I just wanted to show that the other definition that we had for the previous theorem, the other way of writing it, that dy dx is 1 over the reciprocal of dx dy. So here, if I have my function y equals x to the 1/3 and I want its derivative, I could take this relationship and rewrite it using inverses. I could say cubing both sides, y cubed would be x. And then if I differentiate both sides with respect to x, then on the left side I'd have 3y squared times dy dx, and on the right side the derivative of x with respect to itself is just 1. And now I can solve and find that the derivative with respect to x is 1 over 3y squared. And going back, reminding myself y was x to the 1/3. So that's really 1 over 3 times x to the 3rd squared, which is same derivative that we would have had, again, by power rule, 1 over 3x to the 2/3. So I think the big strength here is, if we have a function whose inverse we know, we can use that to figure out what its derivative is, even if maybe we don't already have a differentiation rule that would apply to that particular function. And I'm sure you can guess where we're going with this. We know a differentiation rule for natural log, and hopefully we're going to be able to use that to figure out the derivative of whatever the mystery inverse is of natural log. Now, the nice part about the previous theorem is it doesn't even really require you to know what the inverse is as an equation if you're just looking for the derivative at a point. So here I've got this function, x cubed plus x plus 1, and I am just making a little side note to myself here that there's for sure this one obvious point on this curve, f of 1 is equal to 3. So just first off to note here, this is definitely going to be an invertible function, and the reason I know it's invertible is because it's one-to-one, and the reason I'm going to know that it's one-to-one is because it's strictly monotonic. If I were to look at the derivative for this function, I would see that it's 3x squared plus 1. And for sure, I mean, 3x squared is always going to be 0 or larger, and then plus 1 means this whole function is always going to be 1 or larger. So my function is always strictly greater than 0, which means f is always increasing. And if you're always increasing, if you are a monotonic function, strictly monotonic, then you're going to be one-to-one. So hooray for me, we're a one-to-one function. And that means we are therefore invertible. So f inverse definitely exists, except now the sad news is the equation for f inverse would actually be terrible. If you wanted to try to find it, you'd be looking at trying to solve where x is equal to y cubed plus y plus 1. So if we did our exchanging x's and y's and trying to solve for y, that's what you'd have to do. There is a formula, kind of like the quadratic formula, that can be used to solve cubic equations. The formula is about a dozen times uglier than the quadratic formula. So although it's theoretically possible to come up with some sort of an expression for whatever this inverse is, I personally don't want to find it. And I don't actually need to find it because I'm only interested in, at the very end of it all, what is the derivative of this inverse when x is equal to 3. So I need to know what is the y value when x is equal to 3. And actually, I kind of already know the answer. And that's because since f of 1 itself is equal to 3, then f inverse of 3 should be equal to 1. So I'm actually pretty much ready to go here because I know from my previous theorem that if I'm looking for f inverse's derivative at 3, that would be 1 over the derivative of f at f inverse of 3. And f inverse of 3, we just figured out what that is. The y value there is 1. So really, I'm just looking at 1 over the derivative of f at 1. And conveniently enough, I already figured out what the derivative of f is. It's 3x squared plus 1. So f inverse at 1 would be 3 times 1 squared plus 1, which all adds up to 4. So for my inverse function, even though I don't actually have it, I don't have an equation for f inverse at all, but I'm still able to find out that its derivative at 3 is actually 1/4. So you can sort of guess where we're going now. I mean, we haven't officially said that there's an exponential function out there that's the inverse of natural log. I mean, I'm sure we all know it in our heart, but we haven't sort of officially proven it yet or stated it yet. But even though we don't actually have an exponential function to rely on yet, we can still figure out what its derivative will be when x is equal to 1. So, of course, we already know how to find natural log equal to some rational number. So from before, because of the properties of natural logs that we had proven, we were able to say that we knew that natural log of x, if it were equal to some rational number k, that the mystery x that we're looking for must be e to the k. So if I'm thinking about using that idea here, I mean, I need to figure out what my derivative is of f inverse at 1. So I need to know what is f inverse of 1. That's my mystery question. And so I happen to know for natural log of x what I would put in for its input to give me an output of 1. I know that for natural log of x, if I put in e to the 1, I would get 1 is the output. So that means f inverse of 1 should be e to the 1. And we'd also sort of remarked earlier in a previous section that for any rational number, if you're looking at natural log of e to the k, it would give us k. So if we're looking at f inverse of any rational number k, that would be e to the k. Okay, so let's use this here. I'm going to make my little side note to myself here that I know that f inverse of 1 is equal to e to the 1. I'll make that my little note to myself. And using my previous theorem, I know that I will have an inverse for natural log because it's a one-to-one function, and I know natural log is differentiable everywhere on its domain, and its derivative is never 0, which means the inverse will always be differentiable. And so that means I can now apply the previous theorem and say the inverse, its derivative at 1, should be 1 over the derivative of f evaluated at f inverse of 1. And f inverse of 1, we just said that that was e to the 1. And for natural log of x, we know its derivative. Its derivative is 1 over x. So I'd have 1 over e to the 1. And that would turn out to be just e to the 1. And I could repeat the process again. I mean, for looking at the derivative of f inverse at 2, I'd say in the same sort of way as before, f inverse of 2 should be e to the 2, and that's because natural log of e to the 2 would be the thing that gives me 2. And if I'm looking for f inverse's derivative at 2, that would be 1 over the derivative of f at f inverse of 2, and f inverse of 2 is e squared. And the derivative of f is 1 over x, so I'd have 1 over e squared, which is e squared. And at this point, I mean, you're sort of noticing the pattern, hopefully, that for whatever number we seem to have, the derivative is e to whatever that number is. So maybe we might want to generalize. And right now, we're only generalizing because we haven't officially proven that powers make sense when they're real powers yet. We will get there very shortly. So here I'm going to just extend it one step further and say if we're looking at the derivative of f inverse for just any rational number k. I know on the side that f inverse of k would be e to the k, and that's because natural log of e to the k would be k. So, using my previous theorem, if I want the inverse function's derivative at k, that would be 1 over the original function's derivative at f inverse of k, which is e to the k. The derivative of f, that's the derivative of natural log of x, that's 1 over x. So I get 1 over e to the k, which is e to the k.